Good morning, everyone, and welcome to Friday's Happy Math Hour. Again, we always love to see students join us to review concepts of your Math 1314. Now, I believe today's session we will be breaking up into two groups. For those of you who are want to go over Math 1314, the college algebra, stay here. For those of you who are going to do the Math 1324, the Intro to Business Math. There is a link on your chat. Go ahead and click on that, and Mr. Isasi will be covering that session. So I'll give a couple of seconds for students to transfer over to the other room to go to the Math 1324. All right, perfect. So for those of you who are staying here, again, we will be covering standard form of quadratic equations and graphing. So again, if you have any questions, please put them on the chat, raise your hand, or just open your mic, and you're welcome to stop me at any time with any questions you may have. So let's go ahead and get started. Um, so first, let's go over the standard form of a quadratic equation. Now, the standard form is the second line. It's the f of x is equal to a times x minus h to the second power plus k. Now, you've seen this format already from chapter 1, but we really didn't focus on the name. The first equation, we consider that the general equation. And again, but both of these are representations of a quadratic. So let's go through the definitions of what a quadratic function is. So a quadratic function is in this form, ax to the second plus bx plus c, where a and b and c are real numbers. Our variable x, again, refers to our graph, okay? And then this is a quadratic function. The shape of this quadratic, or the shape of any of these functions, is this U-shaped parabola, right? It's called a parabola. And again, we've covered this quadratic in chapter 1. Our parent function is f of x is equal to x to the second. Now, hopefully all of us can see it doesn't matter in what um, form the quadratic equation is given. Um, Hopefully by now we can see that if we see a exponent of 2 or a highest exponent of a number 2, we know that we're dealing with a quadratic function, okay? All right. So let's look at these two quadratic functions. Again, in general form, ax to the second plus bx plus c. If you see the first one here, the first one, our a value is a positive value. So since our a value is a positive value, our parabola is going to be pointing upwards, okay? We know that this is an even function, so this is another way to also know which direction the parabola is pointing. And again, because it's an even function, it's pointing upwards on both the left and the right of the graph. And on the second one here, we see that our a is a negative value, or we have a negative in front of the x squared. So our parabola is going to be pointing downwards, okay? All right, so again, this is a more straightforward definition. When a is greater than 0, our parabola is going to be opening upwards. When a is less than 0, our parabola will open downward, okay? Now, the vertex for both is going to be 0, 0, okay? The only thing that happened by a being a negative value, we created a reflection on the graph, okay? Now, to do a little review, when our a is a positive value, our vertex is considered to be our minimum point, okay? Our relative minimum point. And when our a is negative, our vertex is considered to be our maximum point, okay? Now, what's a new introduction from this chapter 2 is we have new information to help us better understand quadratics and better deal with them. So we have a formula now that allows us to find the vertex of any quadratic if the function is given in general form. And to do this, we have to find the x value of the vertex of a quadratic, you're going to do minus b over 2a. That will give us the x value of the vertex. And to get the y value, all we have to do is plug in this result, the negative b over 2a, plug it back into the function, and that's going to give us our y value of the vertex. Okay? So this is a new tool to help us find the vertex. Okay, so a new topic that we're also covering with the quadratics in this chapter is before in chapter 1 you were able to find the type of symmetry that a function has. But now we're going to be more specific and we can find that equation of that axis of symmetry for functions. So for us on the quadratic, the axis of symmetry is going to be, you see, the x value of the vertex. Okay, when you're going to be graphing these on the computer, your homework will be asking you to plot the axis of symmetry. Because this is an imaginary line, you're going to use a dashed line to represent your axis of symmetry. And again, the equation of the axis of symmetry is given by the x value of your vertex. Okay. All right. So again, um, we've seen that we have been dealing with quadratics in general form, which in this form, ax to the second plus bx plus c. But again, we now introduce the actual name of this form of ax minus h to the second plus k, which is called the standard form. And we love this form because just by looking at it, we know a lot of details. We know that just by looking at it, that h and k is the vertex of the parabola. Okay. All right. So one of the things that we want to do, let me see if I didn't skip one. One of the things we want to do that will be helpful, as you can see, if we just look at the quadratic in its general form, we don't know much about it other than maybe its y-intercept, because c is its y-intercept. But as far as where the vertex is or what the graph looks like is would be hard to tell in this form. So what we want to do is convert this quadratic from general form to standard form. And this process is called completing the square. So I'm going to go ahead and demonstrate how to do this factoring technique, which is called completing the square. So step 1, we need to factor out any coefficients of x squared that is not 1. So if a is not 1, we need to factor that value out for it to be 1. And again, we are only going to factor it to the two terms that have the x. You're not going to touch the c. You're only going to touch the one that has the x. Now, if by factoring out that term from the a is a factor of all a, b, and c, then you can do this. But on most of the cases, we're only going to factor just the two terms that have the x. Okay, so once we do this, we're going to end up with x squared plus b over ax. Again, the value now in front of the x squared is just 1. So now what we're going to do is we're going to take half of b, okay, and square it. Okay, so whatever this value was, b over a, we're going to take half of it, and then we're going to square it. Okay, so this is the formula that I have here. Then once we do this, um, we're going to take it outside of the parentheses. So if we take it outside of the parentheses, we have to give back the a that we had factored originally from just the two x terms, right? So once we do that, take it outside of the parentheses, we're going to add it to the c part that's by itself. Okay. Now, again, this might be a little bit of information. I'm just giving you a detailed schematics on how to complete the square, but it'll make a lot more sense when we actually look at an example with real numbers. Right now, I'm just giving you just a generic view on how we do this, okay? But again, so once we do this, you'll see that this is a very easy process. So once we do this, we would have completed the square. And what we're going to have is we're going to have our h and k values now. Again, the b over 2a will represent or h value, and the subtraction from c and the minus a times the b over 2a squared will give us our y value of the vertex. So let's go ahead and see an example with real numbers so it can make a lot more sense. Okay, so you will have homeworks and you will be tested on this coming for the second exam for those of you who are coming up on the pre-calc 1. You're going to have a question that says write the quadratic function in standard form and identify the vertex and axis of symmetry. So again, in this format in general form, we really can't tell much about it other than we know that it has a y-intercept at 1, right? But as far as the vertex and axis of symmetry, we cannot see it in this form. So let's go ahead and complete the square. So let's first step that we're going to do is we want to isolate just the two terms that have the x. So this is x squared plus 2x. Those are my two terms that just have an x. Okay. Um, and I'm going to leave the plus 1 outside these parentheses. So now I'm going to complete the square. Since a was 1, I can go ahead and just take half of b, which is 2. 2 divided by 2 is 1. And then I'm going to square that, 1 squared. So that's 1. So 1, if I had a 1 value, this result is going to allow me to complete the square. Now, I already have that 1, so there's nothing for me to add. So I'm not going to add anything because I already have the 1. But again, just to show you in case that we didn't have the 1, then normally what you would do is we're going to be adding a 1 in case that we didn't have it already. But we want to always balance our equations. We can't just add a number just because we feel like it. So what we will do is we would do 1 minus 1. And if we did this math operation, 1 minus 1 is 0, so we're really not adding anything to the problem, um, because when we add 0, we don't unbalance our equation, yes? So when we do 1 minus 1, again, that is 0. Um, and as I had mentioned to you, we already had the 1. So the 1 is already part of our completing the square. So we don't have to do anything to that. Um, so now what this means is that our x squared plus 2x plus 1 is a perfect square. This means that this can be rewritten as x plus 1 times x plus 1. And again, these are two terms are identical, so we can put them as x plus 1 squared. Okay, so now we can see that our ancient, oops, my computer is working a little too fast. Okay, so now we can see that our vertex is um, -1 and 0. Okay, now why is it a -1 if it says plus 1 on there? Remember thinking about solving for the x-intercept. If I have to solve for that x-intercept, I have to move that 1 to the other side, so I have to subtract 1 on both sides. So when you're looking at this in standard form, you gotta make sure that you're doing the opposite value, right? So it says plus 1, but our vertex is located at the -1. Now there is no h value, and again, I put a plus 0 on there. It's not necessary, but that was just for you to see that there is no h value. So our y value is 0. So our vertex is at -1, 0. The equation of our axis of symmetry is the x value of our vertex. So this would be x equals -1. And that's why, again, we love the quadratics in standard form because it allows us to see the vertex and also have the axis of symmetry. So let's look at another example. Write the quadratic function in standard form and identify the vertex and axis of symmetry. So on this one, if you notice, we don't have a 1 for a. So we're going to have to factor in and do some extra work. So let's go ahead and get started. All right, so the first thing that I do is I'm going to isolate the two terms that have an x, the 2x squared plus 8x, and I'm going to factor out a 2 from the first term, okay? So when I do that, I have 2, I factor out a 2, and inside the parentheses, I'm only going to have x squared plus 4x. Okay, so I'm going to take half of 4, which is 2, and then I'm going to square it. Okay, so the number that creates a perfect square to inside my parentheses is a value of 4. So again, I don't want to unbalance the equation, so I'm going to add 4 and subtract 4. That's like adding 0. Okay, so then what I'm going to do is I'm going to borrow just a positive 4, and take out the negative 4 outside the parentheses. But because I'm taking it out outside the parentheses, I got to give back the 2 that I had taken out originally from the factor. So I need to multiply 2 times negative 4. That's going to give me the negative 8 outside. So now I can just add these two values, the negative 8 plus 7, and it's going to give me a negative 1. Okay, now again, by me doing the x squared plus 4x plus 4, um, I know that this is a perfect square. This is the same thing as rewriting it as x plus 2 times x plus 2. But students always ask me, Mr. Carrizales, how do you know that x to the second plus 4x plus 4 became x plus 2 times x plus 2? And the answer is easy. Um, if we look at back on when we're taking the half of 4 and squaring it, before we squared it, that value was 2, right? So that's how I know that it's an x plus 2 and x plus 2, because before it got squared, that value was 2. So I know that's what makes a perfect square. And again, we'll see some more examples so you can see this process, okay? So once I have the x plus 2 times x plus 2, I know I can rewrite that into 2 times x plus 2 squared minus 1. And now, by it being in standard form, I've completed the square. I can easily see what the vertex is. The vertex is negative 2, negative 1. Again, my x value is negative 2. My y value is negative 1. Now, on this one here, why is my y value just negative 1 and didn't change to a different sign? Well, on that one's already on that side, right? If I would get rid of everything that has x, remember that f of x is replacing what y equals to. So y equals negative 1. It's already telling you the correct position of that vertex. So again, the vertex is negative 2, negative 1. The axis of symmetry, again, the equation is the x value of the vertex. So that would be x equals negative 2. Okay, so again, if you have any questions, please let me know. Let's go ahead and look at another example. Okay, write the quadratic function in standard form and identify the vertex and axis of symmetry. So again, we have a function, a quadratic function that our a is not 1. So we're going to have to factor this out. Now, um, I see that all three terms are a factor of 5, but again, just so I don't break habit and just so you can see how my model is working, I'm not going to factor it. I'm just going to factor out the first two terms, okay? So I'm going to isolate the first two terms and I'm going to factor out a 5, okay? So when I factor out a 5, this gives me 5 to the 5 times x squared plus 3x. So I'm missing the perfect square, or the term to make this a perfect square. So I'm going to take b, which is 3, divided by 2, and square it. Okay. So now again, keep in mind what is the value of the term that is before it's being squared is 3 over 2. Okay, so just keep that value in mind, 3 over 2. So 3 over 2 squared is 9 over 4. So to complete the square, I'm going to add 9 over 4 and subtract 9 over 4 to make my equation balance. I'm really adding 0. I'm going to borrow that positive 9 over 4, and I'm going to take the negative 9 over 4 outside my parentheses. Because I'm taking it outside my parentheses, I got to give back the 5 that I had factored out. So a negative 9 times 5 gives me a negative 45 over 4. Okay. Um, so after um, oh, first, again, if you see here, the x squared plus 3x plus 9 over 4, that's a perfect square. That's x plus 3 over 2 times x plus 3 over 2. Again, the value that I had pointed out to you before it got squared. Now, outside the parentheses, in order for me to add those two numbers, I need to have a common denominator. So I'm going to convert the negative 5 into negative 20 over 4 because negative 20 over 4 is negative 5. So now I'm able to add those two fractions. And voila, I have my function now in standard form, which is 5 times x plus 3 halves squared minus 65 over 4. Now I'm able to see what my vertex is. Again, my h value is 3 over 2. That's the negative 3 over 2, excuse me. That is the x value of the vertex. The k is negative 65 over 4. That is the y value of the vertex, negative 65 over 4. And again, the equation of our axis of symmetry is the x value of the vertex, which is negative 3 halves. Okay? So easy stuff, hopefully. Um, this makes a lot of sense now. All right. So, um, again, as I explained earlier, this is just a recap as far as on how we can do it using the formulas. Again, you are going to get the x value of the vertex is basically b over 2a. Okay, when you square that and add it to any c values that you would have and simplify, you'll end up with its standard form. Okay. All right. So now let's look at this one. Now let's get the standard form just from a graph. And this one I think it's a lot easier because it's giving us everything that we need. So the question says, write the standard form of the quadratic function whose graph is a parabola shown. So here we see that they're giving us the vertex. The vertex is negative 1, negative 1. Okay. Um, and I know that I have a y-intercept at 0, 0. Okay, so those are the 2 points that are being labeled. But with these 2 points, I can come up with the standard form of the quadratic equation. So again, the things that we need to know this equation. The standard form equation is given by a times x minus h squared plus k, where our vertex is hk. So, and we need at least one additional point, which again, they gave us. And if all possible, the easiest point to always use is if there's a point that goes through the origin 0, 0, that's the ideal point we want to use, which is what we have right now. All right, so let's go ahead and get started. Um, so we see here that if we have the equation in standard form, h and k refers to the vertex. So our vertex on our problem is negative 1, 1. We have an additional point, which is 0, 0. So now we can just plug in the values to come up with the equation. So again, here we have y value is 0. Okay, so that is represented by the f of x. We don't know what a is, but we know what h is, which is a negative 1. We know what k is, which is also a negative 1, and then we're going to simplify. So once we simplify, um, a negative times a negative is a positive, so 0 plus 1 is just 1. 1 squared is just 1, so we have a minus 1. We're going to subtract 1 on both sides. So we have a is equal to 1. So now we have our equation. Our equation for this graph is f of x is equal to x plus 1 squared minus 1. Okay. So again, for us to do this from a graph, we need to know the standard form um, equation of a quadratic, and we need an additional point. Okay. All right. How about in written? No picture this time, but it's the same process, right? The standard form of the quadratic function whose graph passes through the given point and given vertex. So our vertex here is negative 3, negative 15, and the point that they're using are giving us is this 0, 3, where x is equal to 0, y is equal to 3. So we will do the same thing as before. We're going to substitute what we know. Okay, so we know h is negative 3, k is negative 15. We know x is 0, y is 3. Okay? All right, so when we plug this in, let's go ahead and simplify. Um, a negative with a negative is a positive. 0 plus 3 is just 3. 3 squared is 9. Um, we're going to subtract 15 on both sides. Sorry, add 15 on both sides. So 3 plus 15 is 18. And now divide 9 on both sides. So a is equal to 2. So now we can write our equation, um, which is 2 times x plus 3 squared minus 15. Okay. All right. Again, hopefully I'm not going too fast. Again, if you have any questions, please let me know. Raise your hand or just go ahead and unmute your mics. Okay. So now what we want to do is um, find the x-intercepts. You will have questions on your homework to find the x-intercepts. And to find the x-intercepts now in standard form is a lot easier because we can just use our square root property to solve for x-intercepts. And again, if we want to find the x-intercepts, what we need to do is set y equal to 0. So let's go ahead and look at an example. And again, methods for solving quadratic equations. Again, solving quadratic equations means finding the zeros. Or methods for solving quadratic equations also means finding its intercepts. Okay, all these mean the same thing, and there's several ways of doing this. Okay, again, the method that we're going to be using when we have it in standard form would be our square root property. But that always can't be used. Again, if they give us the equation in general form, then we need to factor it. But sometimes factoring doesn't work. So guess what? In this chapter, we're going to introduce a method to find these x-intercepts or to solve for a quadratic equation that will always work. And this is called the quadratic formula. Okay. Now, um, so let's first solve using our square root property. Okay, and then we'll do the last one. We'll use a example of using our quadratic formula. And I think most of you already know the quadratic formula, or you remember it from high school. Yes, but we'll practice it here. So let's first solve for this function x squared minus 4. And again, to solve for this, we're going to use our square root property. So the first thing we're going to do is we're going to add 4 on both sides, and we're going to take the square root of both sides. So when we take the square root, um, of x squared. Again, most people say that they cancels the square, but what really happens is that that exponent becomes 1. So it really is x. Now the square root of 4, keep in mind when we're doing the square root, we're always going to have two values if it's a perfect number, right? Square root of 4 is positive 2 and negative 2, right? Because a plus 2 times a plus 2 gives me a positive 4. And a negative 2 times a negative 2 also gives me a plus 4. So the square root of 4 is plus or minus 2. This is what x is equal to. So we have two solutions for this function. X equals 2 and x equals negative 2. How about the second one? The second one, again, is what I had mentioned to you before, is in standard form. So because it's in standard form, I can use my square root property again. So the first thing I'm going to do is I'm going to add 27 on both sides. Or first, sorry, the first thing I need to do is set it equal to 0, right? Set y equal to 0. So 0 is equal to 3 times x minus 4 squared minus 27. Then I'm going to add 27 on both sides. Then I'm going to divide by 3 on both sides. And then I'm going to take the square root of both sides. Okay. So again, when I take the square
I'm from Colombia.
Yes, ma'am. Go ahead.
I'm not able to hear you.
Do you hear me?
I
You
hear
have your
you.
microphone on.
Do you hear me?
Yes.
I'm from Colombia.
Okay. Here is the question. Okay. Um, because I'm going to ask something like
Excuse
that
me.
to all of you.
Hello.
Leslie,
Um,
why are you here in the United States?
excuse me. Um, did you have a question for me? Okay, I guess they cleared their mics. All right, there we go. Sorry for the interruption. Let's continue. Um, so when I take the x minus 4 squared and take the square root of that, it's just going to give me x minus 4. When I take the square root of 9, that's going to give me a plus or minus 3. I'm going to add 4 on both sides. So I'm going to have two answers. When 3 is a positive value, 4 plus 3 is 7. When 3 is a negative value, 4 minus 3 is 1. So my solution for the second one, um, oops, I didn't write it as simplified, but the solutions are x equals 7 and x equals 1. Okay, so this is examples of using our square root property. Okay, so there we go. Now let's do an example of factoring. Okay, so on this particular example, f of x is equal to x squared minus x minus 6. Again, the first thing that we want to do is set it equal to 0. That's by setting our y equals to 0. Okay, and we call this a simple factoring. Okay, the way I do these types of factoring is I say to myself, I need to find two numbers that when I multiply them together give me negative 6. And when I add the same two numbers, give me a negative 1. So what I just did is the two numbers I multiplied to give me the value C, and the same two numbers give me the value B. Okay, so what are those two numbers? Well, negative 3 and a positive 2. A negative 3 times a positive 2 gives me a negative 6, and negative 3 plus 2 is a negative 1. So this factors into x minus 3 times x plus 2. Now we can do our zero property that when we multiply two numbers, the only way we can get 0 is if x minus 3 is equal to 0 or x plus 2 is equal to 0. So it's easy to see that our solutions are x equals 3 and x equals negative 2. Okay, this is one form of factoring. Um, oops. Um, there we go. So now let's use our quadratic formula. Okay, again, sometimes we're not able to factor, or sometimes we're not able to use our quadratic, our square root property to find the x-intercepts or to find the solutions. But the quadratic formula will always give us a way to find these x-intercepts or solutions. So this formula is given by this. X equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay. Okay. All right. So this is our quadratic formula. So basically on this one is just plugging in and solving. So the first thing when we are giving the function x squared minus 2x minus 8, we need to know what our a, b, and c values are. So hopefully all can see that a is 1, b is negative 2, and c is negative 8. So I'm going to plug in those values. Minus a minus b, which is a minus 2, plus or minus 2 squared, minus 4 times 1 times negative 8, all divided by 2 times 1. Okay, so if we simplify this a little bit, we have a plus 2 plus or minus the square root of 4 plus 32, all divided by 2. So 4 plus 32 is 36. So the square root of 36 is plus or minus 6. So we're going to have two solutions, right? So we can 2 plus 6 and the 2 minus 6, right? So when we have the 2 plus 6, that's going to give us 8. 8 divided by 2 is 4. When we have the 6 as a negative number, 2 minus 6, that's going to give us a negative 4. So a negative 4 divided by 2 is that negative 2. So those are our two solutions, x equals 4 and x equals negative 2. Okay. All right. Any questions on completing the square, solving for quadratics? Awesome. All right. So that was 2.1. So let's go into section 2.2. Okay. So what we're looking at in section 2.2 is analyzing more of these graphs of polynomial functions. So what is a polynomial? Okay. So again, there's several things. A polynomial is an expression, right, that has many terms, right? This is what this polynomial stands for. Poly means many, nomial means many numbers or many terms. Okay. And when we're looking at a graph of a polynomial, we were always told it's a graph that when we graph it, we don't lift our pencil, right? That means that there is no breaks. no gaps, no jumps. It's a smooth curve, right? And there's no sharp turns either, right? They're smooth curves, right? This is what the definition of a polynomial is, or the graph of it is. It's a um, smooth curves, right, on our graph. So again, if we have breaks, as we can see here, this graph continues, right? The the filled circle means that that value is included, but the open circle means that it's not included. But there was a break, so hence this is not a polynomial. Okay. All right. So here, what is a polynomial? Let's look at these two graphs. Is the first one a polynomial? So on this first one that we see here for A, um, we see a smooth curves. There's no sharp turns. There's no breaks. There's nothing on there that indicates that that's happening. So the first one is a polynomial. But if we look at the second one, there is no breaks on this one, but there is a sharp turn, right? It goes um, going from down to up, like abruptly, right? So this one, because it's a sharp turn is not a polynomial. All right, so now let's look at more details that will let us know or allow us to graph polynomials. So the first thing that we want to do is look at what's called the leading coefficient test. So um, we're going to look at two types of behaviors, one for even functions and one for odd functions. Okay, so let's start with the even functions first. Okay, so the leading coefficient test says this: if you are given a function that is even and its leading coefficient is a positive value, okay, then the graph uh, is going to point upwards both on the left and the right, or the way the book explains it, the end behavior of the graph is going to be rises from the right and rises from the left. Okay. If the for an even function, the leading coefficient is a negative value, okay, then the end behavior is going to fall on the right and fall on the left. Okay. Now let's look at a odd function. Okay, an odd function. Hopefully, we all can determine whether a function is even or odd. Remember, all you have to do is look at the exponent. Since on this example, I'm looking at a cube function, that 3 is an odd number, so that's what makes this an odd function. Now, the leading coefficient test says for an odd function, if the leading coefficient is a positive value, its end behavior means that it's going to rise on the right and fall on the left. Now, the way I like to tell students of end behavior of an odd function is that if it's positive, it means that the graph is increasing always. Like if we, you know how we're supposed to read graphs from left to right, we see that this graph is continuously going up and up and up. So that's how I know it's end behavior, that it's going to fall on the left and rise on the right. Okay. So inversely, if my leading coefficient is a negative number from an odd function, its end behavior is going to be represented by rising on the left and falling on the right. And again, just as before, the way I like to think of these, because I read graphs from left to right, if my leading coefficient is a negative value, or my A is negative, it's always decreasing, right? The graph is going down, 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 all the way down to infinity all the time. So this is what's called the leading coefficient test, and this will help us graph polynomials that we don't know. Okay, so let's look at this first example. Um, Describe the left hand and right hand behavior of the graphs of each of these functions. So if we looked at A, we have never seen a function with a degree of 8, right? This is the highest exponent. So I really wouldn't know what this graph looks like, but with the leading coefficient test, I know the behavior of what this function probably looks like. So let's go ahead and look at the first one. 8. A8 is an even number, so this is an even function. Um, if I look at its leading coefficient, which is 3, this is a positive value. So then for A, the the using the leading coefficient test again, this is an even function, and since the leading coefficient is a positive, okay, that means that my answer is going to be this first one. The end behavior is going to rise on the left and rise on the right. Okay. Um, let's look at B. Okay. B is an odd function, and I know that's an odd function because the highest exponent is 3, so that 3 is an odd number. And then I look at the leading coefficient. I see that the leading coefficient is a -1. So then that means that when I'm looking at an odd function where the negative for a leading coefficient is going to rise on the left and fall on the right. Okay, so it's that example from my templates that the book gives me. Okay, let's look at C. C is an even function. Okay, so its leading coefficient is 1. It's a positive value. So again on this one, oops, my circle should be on the first one, shouldn't be on the second one. This is not pointing down, okay? Unless I, no, yeah. It should be the first one. The behavior should be increasing from the left and should it be increasing from the right. Now, the last one, the D, um, is an odd function, okay? Don't, if I would distribute that -2, okay, that's going to give me my leading coefficient. But first, I need to see what type of function it is. And the highest exponent that I see is a 3, so this is an odd function. And if I would distribute that -2, it's going to make my leading coefficient a negative. So what that means is that now my graph is going to be like this. It's going to be rising from the left and rising from the right. Okay. Um, oh, Ms. Chuka, thank you. See, I'm not paying attention. Let me go back, guys. Let me do a correction of what I said. Okay. This C one, it is correct. And why is it correct? Because the leading coefficient is not 6. I'm not paying attention. Here, my leading coefficient is 8. That's the highest exponent. My highest exponent is 8. Um, so the leading coefficient is a -4. Again, it's still an even, so I had gotten that right. But the leading coefficient is not 1, it's -4. So that's why the graph, the end behavior is pointing to the left and pointing to the right. Thank you for that. Again, I should take my time and pay attention. So please don't do this mistake on your test, right? Always look for the highest exponent to see the degree of the polynomial. Perfect. Thank you for that. All right. So now let's look at these graphs. Observe the following graphs and determine if the graph crosses or touches the zeros. When do you think the graph will cross the zeros and when do you think it will turn around? So what we want to do is, as you can see, sometimes we have x-intercepts where the graph crosses the x-axis, and there's sometimes where it just touches the x-axis and then turns around. And there's a way for us to determine when this happens. Okay, so let's look at this first example. The first example here, the one in green, where we have this graph that is crossing the x-axis here at -1. It turns, it crosses the x-axis again completely at 2. It turns around and it crosses the x-axis at 4. Okay, so if you look at this graph completely crossed the x-axis. And if we look at the factors of this function here, we would see here that we have x minus 2, x plus 1, x minus 4. We have all individual values. These values for x equals 2, x equals -1, x equals 4. None of them repeat. So what that means, if none of them repeat, that means that the graph is crossing completely our x-intercept. But if we look at this other example, see, we have this one in orange, where we have a graph that it's increasing, but then it touches the x-axis. This is considered an intercept at -2, 0, but it doesn't cross it. It bounces back, turns, and then it crosses here at 2, 0 completely, right? And if we will look at this equation, again, if we will look at this in general form, x cubed plus 2x squared minus 4x minus 8, if we would find the zeros, we would see that we have a duplicate, or we have two of them that are the same. X equals -2, x equals -2, and x equals 2. So when you factor out the zeros or solve for the zeros, if you have duplicates, what that means is that it's going to only touch the axis. It's going to touch, and turn around. Okay, so let's look at this purple one. Okay, looks like a W, right? So I see here that it crosses at -2, it touches at 0, 0, and then it crosses at +2. So again, if I were to solve for the zeros here, I would see that my zeros are x equals 0, x equals 2, x equals -2, and x equals 0. Since I have a duplicate of x equals 0, that means that it's going to be represented as touching on my graph. Okay, so whenever you have duplicates, also the way your homework represents these touching is called the multiplicity. Okay, so when I have a multiplicity of 1, that means it's crossing completely the graph. When I have a multiplicity of 2, that means that the graph is touching, that we have duplicate values for x. Okay, so just something to keep in mind. All right. So, got ahead of myself. So let's more detail as far as what I just said, the multiplicity of zeros. So the multiplicity of zeros will be determined whether the graph crosses the x-axis or it just touches the x-axis. Okay. So if we look at this first example here, what does multiplicity means? And so it means the number of times that the zero occurs. Okay. So here, if we notice on our parent function, the x squared, we say that we have two zeros, right? We have a 0 at 0, 0. If we were to solve, x equals to 0 and x equals to 0. So our multiplicity on this is 2, right? So then again, on our example here for our parent function or our q function here, we have at x equals 0, x equals 0, x equals 0. So we have an odd number of times. So therefore the graph will cross at x0, right? So this is what our multiplicity is. It's how many times it's going to cross our x-axis. So let's look at an example. Find all the zeros and determine the multiplicity of each zero. Okay. All right. So on the first one, we're gonna set it equal to 0 so we can solve our quadratic. And let's go ahead and practice using our quadratic method. So on this one here, 0 is equal to x squared minus 2x plus 1. For me, I think the easiest way to factor or to solve for the x-intercepts is by factoring. Again, I want to find two numbers. I want to multiply them together, give me a positive 1. And when I add these same two numbers, give me a negative 2. And those two values are -1 and -1. -1 times a negative 1 is a positive 1, and -1 plus -1 is a -2. So I know that this function can be factored into x minus 1 times x minus 1. So we see here we have x equals 1 twice. So what this means is that z at x equals 1, it occurs twice. So that means that it's only going to touch the graph. Okay. Um, let's look at this example. Find all the zeros and determine the multiplicity of each zero. Um, so the first thing that I would want to do for this one is set it equal to 0 and use one of our quadratic methods. Okay, so the first thing to do is set it equal to 0. And since I see that all three terms share a t and a t squared, I'm going to factor that out. So I have a t squared is equal to, or sorry, it's t squared times t squared minus t minus 30. Then I'm going to factor the inside. Okay, and again, I need to find two numbers. I want to multiply them together, give me a negative 30. When I add the same two numbers, give me a negative 1. What are those two numbers? Negative 6 and a positive 5. So now I can use my zero property to solve for the t's or the intercepts. So we have 0 is equal to t squared, t minus 6 is equal to 0, and t plus 5 equals to 0. So the first one, again, um, doing the square root on both sides, t is equal to 0, t is equal to 6, t is equal to negative 5. So at 0, it occurred twice, so we have an even multiplicity, and therefore the graph will touch and turn. The other ones have an odd multiplicity, the t equals 6 and t equals negative 5. Then that means that the graph will just cross through those 2 points. Okay. All right. And again, if we were to graph this, again, it's hard to see on this graph right here, but it's like a big W. The the W points on the bottom go way below my graph, so you can't see them. But this is what happens at -6. Sorry, -5. It crosses the x-axis. At 0, we had a even multiplicity, so it's a double duplicate, just touching at 0, and we had an odd multiplicity at 6, so it's just crossing the graph. Okay? And again, it's these values here. This is the -5, this is the touching at 0, and it's the crossing at 6. Okay? All right. So now that we know its end behavior, we know what can happen when a graph crosses or touches. Now we're able to graph a polynomial. Okay, so let's go ahead and graph this polynomial. G of x is equal to x cubed minus 3x squared. Okay, so let's go through our information. To be able to sketch this graph, we need to identify its end behavior, find zeros, identify the multiplicity of each zero, find the y-intercept, and if need be, plot additional points to make our graph a little bit more accurate. Okay, so let's go ahead and get started. So first, I see that I have an odd function, and this odd function has a leading coefficient of a +1. So then that means that my graph will rise um, on the right and fall on the left. Yes, so that's the end behavior. And then when I find the zeros, okay, the first thing that I would do is I would factor out an x squared, and then I would solve for them. So I see that I have x equals 0, x equals 3, but the 0 came from taking the square root. So I have a double 0 or a duplicate 0, so that's an even multiplicity. So I know at x equals 0, the graph will only touch and turn. Since 3 is an only 1, it's an odd number, so we have an odd multiplicity, so I know that the graph will only cross at 3. Okay, so let's get the additional information. Um, let's find my y-intercept. I already found my x-intercepts. Now let's solve my y-intercept by setting x equal to 0. So when I set x equal to 0, I see that the y-intercept is at 0, 0. So this helps out. So let's go ahead and graph what we know already. Okay, so we know that we have these um, zeros, and at 0, 0, we have not only it's a duplicate 0, but it's also our y-intercept, and that 3 is just the graph will cross directly at this point. Now, because I knew my behavior of this graph is falling from the left and rising from the right, I can go ahead and draw those lines. Okay, so I know that it's falling from the left, rising from the right. But if you can see here, um, I would need additional points to see what's happening between 0 and 3. Okay, so again, I know that it's just touching at 0, 0, but in order for me to find out what's happening between 1 and 3, I put these additional points that are between 0 and 3. I picked x equals 1 and x equals 2. So when I put x equals 1, the y value gave me a -2. So I went ahead and plot that, 1, -2. When x equals 2, I got a y value of -4. So I went ahead and plot that as well. So these are my additional points. So now I can go ahead and create my semi-smooth line right on the computer. But again, if I would use my Desmos graphing calculator, which would be a nice smooth line, this is the shape. And again, for your homework, it's just good to know what the graph looks like, because again, you have multiple choice to determine what the graph looks like. And again, by knowing all this information, it allows us to determine the graphs. Okay. So again, I hope this presentation helped. I didn't have any comments or questions, so I guess that's good. Just want to remind you as well, if you came in half the way, I saw some people come in half the way of the presentation. We record these sessions. They get uploaded to our YouTube channel. okay, which the link is provided to you there on your chat. Again, thank you for joining me today. I hope you guys keep on moving forward. Have a good weekend. I look forward and looking or seeing your names all next week. Again, thank you all for joining me.
Thank you, Mr. Carizales. Please join us again next Friday for Happy Math Hour, and thank you all for being here today. Next week, we will cover Math 1314 with synthetic division and complex numbers, and Math 1324 will cover solving exponential and logarithmic equations. We do want to remind you all about our previously recorded sessions, as Mr. Carizales mentioned, which are available on the YouTube playlist. The session will also be available on that playlist later on today. Also know that our online tutoring is open now and available through Blackboard Collaborate Ultra 7 days a week with our new hours from noon to 9 p.m. Monday through Sunday, and face-to-face tutoring is available Monday through Friday, 8 to 5. Thank you so much again for presenting, and thank you, audience, for coming and being a wonderful audience. We will see you next week.